All right. So thanks, Bill, for the introduction. Yeah, I'm Mamata Varacharya, Senior Applied Scientist in Etsy. And today I'll talk about recommender systems, overview and trends, and most of my examples will be in the context of e-commerce because Etsy is an e-commerce company. So quickly, a little bit about Etsy. It's a two-sided marketplace where sellers make handmade, unique creations, and buyers come to Etsy for a delightful experience of buying handmade, individually built stuff. And during this weird times of COVID, we are standing pretty heavily with our individual sellers. And we even have a hashtag called Stand With Small. Feel free to check it out. Yeah, so this is just a screenshot from our platform. All right, so overview of recommendation system, right? So given a user, let's say, or a listing, suppose it's a user and this is a listing, we show items that are either personalized to the users or for a given target listing, you see other items that might be similar to that listing. So potentially many of you might have gone to Amazon, visited Amazon.com. If you go to a listing page, you see a product and then you might see you may also like or similar to this particular listing that you're seeing. All that is an instance of application of recommendations. So how do we build this? And how do we build such recommendation? What kind of goes behind the scene? I wanted to motivate and talk a little bit about those aspects and specifically focusing on two pillars. One is around deep learning scope in this area, and another is around more custom objective function. So traditionally, the field of recommendation system kind of became very famous from this particular method called collaborative filtering, which is a form of matrix factorization. And it kind of had this, there was this challenge called Netflix challenge that led to researchers develop this method of collaborative filtering, which essentially does something that was already known in the literature in the space of singular value decomposition. Here's an example. So given this is a matrix of user and movies, the 3 rows represent user preference and the 4 columns represent the movies. So for example, user 1 did not see Matrix, really liked, rated 4 for Pulp Fiction, really liked When Harry Met Sally, rated 5 and did not see Star Wars. Similarly, the other 2 users has the corresponding ratings. Essentially using something like collaborative filtering, we could fill up this missing information by learning some lower dimensional preference of these users in the movies for which they have provided ratings. So the idea is very simple, that we know that user 1 liked Pulp Fiction and liked Harry Met Sally, but did not see Matrix and did not see Star Wars. Could we generalize this content that the user has, information that the user has given us by his or her usage, and extract that some kind of information in the latent space to be able to extrapolate it to some other movies that we don't know if the user would like or not. So a very kind of a toy view of matrix factorization is, imagine this blue matrix, M by N matrix, user to movie matrix. And we could devise 2 smaller, kind of skinnier matrix, M by K and K by N, where the first one, the orange one, is essentially users preference matrix and user preference to a genre. Let's take that as an example. And the green one is movies association with genre. So here, if you think about it, for this large M by N matrix, we somehow figure out to get this skinnier M by K matrix and K by N matrix, where M by K is for a given user, whether the user has certain kind of score that is associated with sci-fi versus crime versus comedy. Similarly, for a given movie, if we know that kind of distribution for the same genre, we can very easily then pick the particular user row and pick the particular movie column and take dot product of it to obtain their preference. So in this case, I'm trying to show that this blue row for the user, and this particular user has never seen this pink call a movie, but we could just do a dot product after we know the latent representation to find what the rating of this user for this pink movie would be. So as you can imagine, this really gives us a way to learn user preference without explicitly knowing how the user has reacted when that product was shown to him or her. But pretty soon the field understood that there are some limitations of matrix factorization. There were some more recent approaches that kind of build on this idea of matrix factorization, collaborative filtering, specifically using deep learning and a more probabilistic approach. So probabilistic linear factorization is such an area, and more leveraging more latent factor models such as multimodal topic models or latent duration allocation as such a topic model that has been used in the space. And then more recently, neural collaborative filtering. However, I'm not going to go very much further in this area, but just wanted to motivate because this is one of the state-of-the-art. Most frequently when someone talks about recommended system, they often talk about, to begin with, collaborative filtering. All right, so now that so going to this matrix factorization zone, as you might have imagined, that there is some other challenges. For example, what about this M by N matrix? We need to know at least some preference of a given user for some movies. And in real world, we don't really have 100 movies. We might have millions and millions of movies, shows, and other kind of documentaries. So this M by N matrix often becomes extremely sparse. It becomes difficult to even learn these kind of lower dimensional representation or these skinnier matrices for the corresponding user product matrix. Hence, we have figured out a different kind of approach instead of going by the collaborative filtering approach, which is referred to in the field as content-based recommendation. And now for kind of motivating content-based recommendation, let's take this example. So let's say in the context of Etsy, we have a personalized recommendation module called Our Picks for You, where we have shown these 5 listings to the user. And we can collect using visit log and other kind of information, how the user has reacted when these items were shown in front of them. And here I'm showing this particular listing, the user really liked it. So she actually purchased it. The next listing, the user favorited it, and so on and so forth. These implicit feedbacks can then be used as labels. So purchase, for sure, in the context of e-commerce could be a positive signal, and impression, which means the user was shown the product but never really interacted with it, could be negative signal. And we could now convert this problem into more of a supervised learning method where we can put in tons of information about the user and about the products, about the listings to predict these purchase versus click versus impression. And that becomes kind of a basic idea of content-based recommendation. So all these information goes into an ML model, and then it produces some kind of probabilities. And in this, you can determine what kind of probability do you want to generate, or what kind of objective function you want to optimize. And in this case, the example I'm showing, let's say we want to optimize for probability of purchase. So as you can imagine, once we have the model learned, we will need to have some kind of infrastructure ready for inference, because I might have a model learned in my production system, but I cannot control when a user will come to the site, right? When a user will come to Etsy.com. So I have to have the model prepared, but have to have a mechanism to make the inference as the user comes in. So here is what a very zoomed out version of how inference happens is, now that we have a model that takes in user data and listing data, we could then generate those feature vectors in real time and basically ask the model to predict those probability scores, the pre-trained model that we have trained, and then it outputs scores. And then we can sort the scores in order that becomes our ranked list of recommendations. And this is kind of motivating this whole space of learning to rank. That's where the concept of ranking comes in. Then again, in reality, in platforms like Etsy, there is even just the content-based ranking is not sufficient, because we have so many millions users. We have more than 45 million users. We have daily active listing of more than 65 million. So it's way too many computations to compute offline or even compute in real time. So we kind of divide this process of generating the final recommendation in 2 stages, which is also pretty much of an industry standard, where given the target, again, going back to the user and listing, we use either a heuristic way or some kind of simpler way to generate a smaller subset of, from the millions of listings, a smaller subset of hundreds of listings, and then use the second pass ranking system that I showed in the previous slide to generate the final ranked list of recommendations. And oftentimes this is referred to as the first one, for the first component is referred to as candidate set generation, and the second component is referred to as the second pass ranker. So essentially, very simply, given these users, the candidate set will select a list of, let's say, 200 items. And the second pass ranker will then sort them in a certain order that can be optimized for a certain objective. And in 2 slides before, I showed you the objective was kind of optimizing for probability of purchase. And so now you can imagine, based on what I just said, that I deliberately kind of kept the ranking part, the machine learning part, kind of vague, because that's where all the research comes into place, that you can really replace a second pass ranker or even the candidate set with tons of different machine learning models. Here is an example where you just take a logistic regression model and feed in all these hundreds and hundreds of listings for a given user, represent the users and listing as feature vectors, and then learn some kind of optimize for some kind of objective that your business cares about. And then you can also imagine that we can replace this particular ranker with a deep neural network as well, and then learn a more generalized, more complex function to learn this relationship between the listing and user preference. So this is where kind of the, I'll talk a little bit about how in production we thought about moving from linear models to non-linear model. And what are really some of the things we need to keep in mind as we start going into more and more complex? Surf is definitely super promising. There's a ton of work that has shown that it outperforms many other kind of linear or even non-linear models. But there are a lot of hyperparameters, a lot of considerations that and a lot of robust experimentation that one needs to do in order to ensure that the model is even each of the layer. How many neurons should be there in each of the layers. Very gradient descent should be enough. If your data is really large, you might have to go to stochastic gradient descent or mini batch. There are many other optimization methods such as ADAM, AdaBoost, and adaptive optimization methods. Then there is other considerations like initializing weights, regularization, early stopping criteria, what kind of activation function should you use, like RLU or purpose. So here is just an example of if your learning rate is correct, then your loss should ideally be reducing with every epoch and every iteration. And then eventually it should stabilize to a very stable state where with more number of epochs, your loss should not continue jumping around. And it's super crucial to be able to look at your loss curve and really assess whether your objective function has at least come to a local optima. Because otherwise, really, there is no stability to the model, and even if you might be seeing good AUC numbers, good accuracy numbers, or precision recall, it doesn't really say anything. Your model is not learning anything if your loss hasn't converged. All right, here I have cited a paper that was published by Airbnb where they kind of speak about their journey in deep learning world. Another thing that I noticed was increasing the size of the data set definitely improves the performance. And here I'm just showing AUC numbers where the blue curve is showing when the model was trained on 60 days worth of visit logs data, and the red curve is when it was trained on 14 days worth of log data. And here it's TensorBoard. If you're using TensorFlow, TensorFlow 2 is amazing. If you're using TensorFlow for deploying your deep neural network or experimenting with deep neural network, there is very stable, good tools that you can use. For example, TensorBoard to assess your model convergence, to look at your metrics, and so on and so forth. Now I'm going to go a little bit into up until the previous slide. I was trying to kind of show something simple, like dense neural network, and it's the most standard way of doing classification. Now let's think about what are some of the other areas where deep neural network has deep learning methods have really helped researchers and ML practitioners to kind of get advantage of data that was not really possible before this real push for deep learning that happened in the near past. So think about this particular beautiful vase. It's a listing from Etsy. We could have tons of information about this particular product, right? Like we could have seller provided metadata, that is the price of the item, the dimension of the item, and so on. We could take information such as historical interaction. How many times it users purchased this item in the last 1 month, how many times the user favored this item, and so on. Then we can really start looking into unstructured data, right? Text, title, descriptions, reviews, and many such unstructured data. We could also start extracting image features based on the pixels, sharpness, quality. All these information with traditional machine learning model, it used to be difficult to be able to inform the model with all these kind of modalities of data. So they're all different modalities. Text is different modality, image is different modality, real value dense features is different modality. With the advancement in deep learning methods, not just learning vector representation of these kind of unstructured data has become possible. We can also easily kind of ensemble all these modalities of data to learn a combined objective function. Here's an example from a paper that has shown really promising result. It's a very simple deep neural network model, but they show that combining these kind of different modalities of data from its raw form to using embedding layers and learning vector representation from these raw data, and then putting an n-layer deep neural network to learn the final objective, worked really well. So this was, I think, sometime 4 or 5 years ago, this paper was published. So since then, there has been many more advancement. But this was just to motivate that this is another promising area in deep learning where multiple modality of the data we can start taking into account, we can start leveraging these kind of different qualities and different characteristics of data and still learn jointly from these multimodal data. All right, another area of deep learning that has been really promising is sequence model. Now, imagine this situation in an online site, in an e-commerce, for example, in Etsy. A user comes in, clicks on an item, clicks on another item, adds to cart some item, and then leaves the platform. Then another user comes, then a few days later, the user comes back and continues clicking and finally decided to purchase something. So as you imagine, this is a sequence of action that the user took, which could be super valuable for us to understand what the user preference is, for any business to understand what the user preference is. So this is essentially a sequence of action. And again, sequence data could be other things. Sequence data could be, for example, text. Text is nothing but a sequence of words. Image could be treated as sequence of pixels. So sequence model is another space in deep learning that has really helped, not just recommendation systems, search models, and many other business use cases as well. And in the space of sequence model, there is tons of research that goes into. More commonly known methods are recurrent neural network and some some improved versions of them, namely LSTM and GRU. And more recently, we have some, especially in the area of attention-based model, we have some really good work coming out from different research labs. Here is an example of a sequence model in the space of recommendation based on this paper. Self-attention sequence recommendation, where we are seeing basically that when the model is told that this user likes item S1, S2, and S3, it's able to predict that the user will next interact with item S4. And as you can see, it's quite related, right? Like a user bought a computer, then bought a mouse and a printer, and then it was recommending papers, printing papers. So this is just an example, and it was purely attention-based model. And here's some of the papers. One of the main attention paper that kind of really kickstarted that field was Attention is All You Need. I think it was 2016's paper, don't quote me on that. That's a really good start if you want to kind of get a hang of what is attention models. All right, and another work that is pretty widely used in industry is called this wide and deep models, where essentially it's a way to kind of memorize part of your data while generalizing some other part of your data, which helps to kind of maintain the balance between accuracy, while if the test case is very different from what your training set is, the model can still adopt because of the generalized component. Not going into further details about it, but check out this paper as well, wide and deep model. And then there are a few other improved versions of it. In fact, Google's YouTube recommendation system uses a similar model for the recommendation. And there is a 2019 dub paper on that. Finally, I wanted to give an example of another deep learning area of research that is pretty exciting, is multitask learning, which is kind of can be thought of as multi-objective learning, where imagine if you're a teacher and there are some common skills that a teacher requires. For example, like some basic math and some basic science understanding and some language communication ability. But then if you're a history teacher versus a biology teacher, you can have different specialization. So this is that's the scope of this multitask learning, especially this kind of architecture, mixture of experts. Essentially, the idea is there's some commonality from the data that all the experts should learn from. And then there are specific parts of the network that are only trained for certain kind of expertise. So here I'm showing an example where there is shared bottom, which takes all the features and all the data that you're providing. But then there are two different towers, one of which is becoming an expert in engagement. So in the context of, let's say, YouTube, you can think of engagement as clicking on a video, versus retention is if a user ended up watching that entire video, completing the video, that's retention. So you could kind of learn about the specific aspect of your data by building these kind of towers for expertise. And this is a space of recommendation which is pretty new, and helping researchers, helping industry practitioners to kind of learn multiple objectives in the same at the same time while leveraging deep learning approaches. So yeah, this is along the same line of multi-objective optimization. I did wanted to see how much time do I have. Bill, how much time do I have?
You have more times, about 10, 15 minutes.
Cool. Yeah, then I can take the next topic as well. Yeah. All right. So so yeah, wrapping up this space of deep learning, I wanted to motivate this multimodal data that enables us to use all these text, image, structured data in our model. Sequence models is another space which has a ton of applications and very active area of research. Multitask learning, mixture of experts is another area. Then there are some other areas like graph embeddings and graph-based learning and reinforcement learning that are also very highly research area and very active area of research in this space. Now I wanted to talk about this one paper that we published last year in Rexis, which is also a real application in the context of Etsy, where joint optimization, specifically in this particular paper, we talk about joint optimization for profit and relevance. Now imagine these 4 items. We could show these 4 items in these kind of orders, for 3 different kinds of order, right? Like the first one shows that the black bowl is shown first, and so on and so forth. The second one shows that the most expensive gray-black mixed bowl is shown first, then the next most expensive item is shown next, and so on and so forth. And then finally, that it's not clear what the order is, because it's, even though the first item that is shown in this ordering seems like it's more expensive than the first row, but it's not just price-based or decreasing order. So I think what I'm trying to motivate here is relevance is something that we are trying to determine in some way by modeling user preference. Even though we don't know what the user would prefer, we are trying to optimize and trying to learn from the data what the user preference would be. And profit or price is something we already know for the item if you're the platform. But just optimizing for profit could be very harmful for you, because you could end up like not showing relevant items to the user. As a result, your buyers might just leave your platform. So here in this study, we proposed a way to kind of incorporate profit or revenue as a part of the objective function while not compromising relevance. So in a simple logistic regression, the objective function is to find maximum likelihood estimate of a model parameter W and B by solving this cross entropy loss. You all might have seen this loss. It's a simple way where W represents the parameters of the model and X represents the data, and beta is the bias. This objective, however, there is nowhere in the objective that the revenue term, right? So this objective does not explicitly maximize revenue or profit. So we introduce this revenue term within the logistic regression objective function by just introducing this additive term, mu times rho of WB, where W again is still the same parameters of the model, and beta is still the same bias, except there is a new additive form of another function, rho, which also does something in addition to the traditional logistic function. So essentially, here, this rho WB is, what is this function? We propose that it's an expected revenue generated by the M recommended items. So it's essentially expectation of pi I times yi, which is pi I here is the price of the item I. And yi is still the same, like expectation of yi is the sigmoid of W transpose xi plus b. So essentially, this last term, sigma of I equals to 1 to m, becomes the additive part of the objective function. So that kind of, you can focus on this second middle row is what we try to jointly optimize. So jointly optimize as in, this is just the objective function. We then use, I think in our case, we use stochastic gradient descent to learn these W's and B. So only difference was, instead of just optimizing for L of WB, we jointly optimize for this joint optimization function. And for any model, deciding on the right evaluation metric is super important. So for this particular approach, we used these three metrics: area under curve, NDCG, which is normalized discounted cumulative gain, which is a common metric used for ranking problems, and then profit at K, which because we were trying to jointly optimize for relevance and revenue, we use this profit metric to determine how much profit improvement, if at all, using the traditional objective function versus using our objective function. And we use multiple baselines, including logistic regression, weighted logistic regression, and linear regression, where for linear regression problem, the Y value was price of the item. And we found that our model with this joint kind of optimization not only improve the profit or improve the relevance, but also improve not only improve the profit, but also improve relevance. So essentially, it was able to surface to the user slightly higher price item while not compromising on the purchasability of the likability of the item. And that's the beauty of joint optimization, right? Instead, if we would have first optimized for relevance and then somehow ranked or somehow changed the order for price, that would have messed up the relevance ranking aspect. And so this kind of framework enabled us to jointly optimize for not only relevance, but also revenue. And here's an example. So the first row is showing the original ranking by logistic regression. The third row is actually showing our final model, where our modeled rank list, where we are seeing a slightly higher price item was ranked first, then the next or third higher price item, and then, but you can clearly see it's not sorted with respect to price as the second row, which was just sorting with respect to price. Yeah, that's all for my presentation today. Thank you, everybody.
All right, great. Well, thanks a lot for the talk. And let's move to Q&A. I think we already have quite a lot.
Okay.
If you can just open up the Q&A, we can go from the top to the bottom. And for any of the attendees, if you want to prefer to speak, just raise your hand. I can let you speak to ask questions.
Okay, so should I just start?
Just read through the questions and go one by one.
Okay. Does use of dropout come under network architecture, or are you not faced with much overfitting? That's a great question. No, definitely overfitting is a problem, especially once you make your model more complex. Overfitting has to be checked for. And as a part of your architecture, you should check, you could include, if there is overfitting, you could include dropout layers. I did not mention specifics about, so there is definitely, even in a dense neural network, you could add dropouts, you could add batch normalization and other kind of layers in addition to your just activation functions. Which optimization will you recommend, especially for production level recommended system? We use Adam. In one of our production system, there are tons of optimizations. Stochastic gradient descent is also one. Adaptive learning. So Adam does adaptive learning rate. That's why it's quite good. There are some other adaptive learning rate optimization methods available in TensorFlow API and any other PyTorch or whatever you're using for your implementation. Okay, which metric would you look at to gauge the accuracy of a recommended system? Yeah, so I guess I showed that at the end. We use NDCG, AUC, you can use precision recall. I would say often for your own task, oftentimes you also have to develop new metrics to kind of ensure that you're evaluating your model for what your business purpose is or what you're looking to evaluate. So we oftentimes end up implementing some custom metrics as well. Does multitask learning imply using wide and deep model? Not necessarily. No, multitask learning is a different area of deep learning research. We potentially could. I don't recollect having seen any work where multitask learning and wide and deep was spoken together. But it could be. Wide and deep is just a way to structure your architecture of the network, while multitask learning is a different kind of idea altogether, where your hypothesis is that there is some aspect of your task that should be uniquely learned by some part of the data. For example, in image classification, if you think that some part of the image could be jointly learned, for example, background, color, and then specifically you want some towers of your network to learn how to classify animals versus some part of your network to learn how to classify cars, one car from another. That could be an example of multitask learning. If there is a new product that is different and unique, then we don't have implicit feedback. Then how will you make sure new product reaches the right customer? Absolutely. So that's whole area is, there's definitely a ton of selection bias that can go into that. Our data is biased, so some of the popular items keeps getting surfaced on the top. There is a lot of emphasis in the field in space of multi-embedded or reinforcement learning, where you kind of introduce a component of randomness, a component of not always optimized based on historical data. that helps overcome some of these problems. How do you evaluate the relative success of alternative recommended system? Is there a system for A/B test on click-through additional purchase rate? I don't know if I completely understand the question, but I'm imagining it's around the offline evaluation metrics, which I already mentioned. And yeah, every company has their own online evaluation system. If they're using A/B test, then it's A/B test. And there the metrics are very different. So it's usually business driven, KPI driven. And all the metrics that I presented here were all about offline machine learning evaluation. I did not talk about, and I don't think I'm allowed to talk about the A/B test metrics that we use. All right, so could you please share your experience with model development in production and challenges which you faced in production, and how do you handle those challenges in general for recommended system? Yeah, so I guess part of my deep learning slides were around that, like what challenges you face. I think as simple as knowing whether your model is learning something is super important. So a lot of emphasis in general is given on how fancy a model is. And oftentimes in real systems, you end up spending maybe 10 to 15% of your time in thinking about the fanciness of your model or objective function. And more often than not, it's what data you have, how to clean the data, how to build the architecture such that, or the system such that it runs in production, working with infrastructure people to kind of think about latency and whether there will be some listings that we need to filter out. So there are all sorts of real world situations that actually takes up much more of your time than the model itself. But as and when you're building model, it becomes very important to have right trackers and right kind of tools to assess whether the model is converging, what kind of hyperparameter values should be provided. And even for any real production system, lot of models doesn't really make sense. So for example, a lot of unsupervised learning methods are actually, during my PhD, I used a lot of unsupervised learning method, but in real production system, it becomes very difficult to really trust a lot of unsupervised learning method, for example, because of the lack of evaluation metrics. So I cannot emphasize enough how important evaluation metrics are, offline evaluation and continuously tracking those offline evaluations as well.
Actually, we have attendees raise their hand for a long time. I want to give him or her a chance to speak, to ask questions. Hi, Lalit. You can speak if you have questions.
Actually, sorry, I raised the hand when you asked the question. If you can see something, sorry, it was from the past. Sorry, but I have a question posted in the Q&A, so maybe you can revisit later.
I see the question.
Okay.
Yeah, sorry. Yeah, I didn't raise my hand down.
Okay, that's fine. Okay, now you can go through the question again.
Okay, so let me take Lalit's question then first. What do you do with user ranking when you calculate profit and relevance? So the joint optimization task of evaluating for both profit and relevance is for item to item recommendations. So it's not for user to item recommendations. So and that was a deliberate choice. We did not want it to rank for profit for a given user. So item to item recommendation is, let's say when you go to Amazon.com and you're looking at a product and then you see other products you may also like or similar to this listing. So that's an example of item to item recommendation. So the the ranked items that we show for that given product uses the joint optimization. Even though now in production we have a different system. We don't no longer use this objective function in production. All right, so hope that answers your question, Lalit. So I'll take the next one. In recommend systems, you usually get item embeddings. Can you comment on the nature of these embeddings in different architecture? I am not sure if I understand. You usually get item embeddings. If you're choosing to use item embeddings as a part of your system, then we have item embeddings, and there's tons of different ways to generate item embeddings. one way is you could, for whatever task you're using, if you have item embeddings, you can use something like approximate nearest neighbor or something to calculate similarities between embeddings of items to generate candidate set. And in various places in our production system, we use item embeddings. Yeah, but usually I don't know if it's if it will be overgeneralization by saying usually, but there are use cases in recognition system where you use item embeddings. How is it doing better than loss function that optimizes only for relevance? Yeah, so I in my slides I had a comparison table. I think the improvement was something around 8% in with respect to AUC and NCG. It would be great if you could elaborate on evaluating the performance of recommended system engines. Yeah, so typically NDCG is the most common metric, which is it's most common because recommended system end of the day is a learning to rank problem, and NDCG inherently takes the rank into account and the position of the item, the rank of the item into account, and that's why NDCG in the literature is the most common ranking, most common metric. There's also other metrics like mean reciprocal ranking, which is another metric which is inversely proportional to the rank of the item generated. And then you can use, of course, use precision recall at K, precision at K, and we also use AUC. So these are, as I said, these are more common metrics, but for your own project's purpose, we often end up also developing new metrics. For example, for the revenue work that I presented, we had some metrics around price and profit. I think we also had a price-based NDCG. All right, I think I already answered Lalit's question as well. So next, let me go to Sam's question. In theory, are expert neural network models any less capable than a complex, regular, single objective neural network? I think the purpose is very different, but in literature, there has been several studies that have shown that if you train for the, let's say for the example that I was showing, if you have two experts as a part of the mixture of expert model, instead of that, if you train two separate neural networks for those two tasks, there is a ton of paper that have shown that the mixture of expert model does better. Of course, this is a specific area of neural network and specific area of research. My advice would be just if you're intending to explore this, you should try out by also independently training two networks separately, and then try out the expert mixture of expert model and see which works better. You should definitely anyways compare with the baseline. But the papers that I have cited and have seen definitely have shown that mixture of experts that work better. What are other areas? What other areas can DNN-based recommendations be applied to? Any area of recommendation, depending on what your purpose is. I mean, I guess I showed with respect to e-commerce, but other areas like Netflix and Pinterest, all these companies use a deep neural network for their recommendations. What are some techniques commonly used for deciding if earlier observation in your data set are no longer as relevant as newer ones? So this is a good question. So there are some active areas across freshness and diversity. So I recollect reading a paper where that there was a part of the objective function. So it was a multi-objective optimization way, and a part of the objective function was incorporating diversity as so it was kind of optimizing for relevance and diversity together. I know there are some Google papers where they talk about freshness as a component. So I think they specifically optimized for freshness. But these are freshness, diversity. These are some very, very, very exciting areas in recommendation because more and more we start relying on machine learning models for recommendations and real applications. The more the models learn to predict certain patterns and things like popularity, things like click-based, they become more and more prominent, and hence things like diversity or freshness or avoiding selection bias becomes very important. So these are definitely exciting space in recommendations that people are thinking about. Thanks for your great presentation. One quick question. Have you needed or incorporated any model interpretability module for ranking/validation? Yeah, great question. So model interpretability, I would say that we do leverage model interpretability, but from like post-modeling context. So after the model is developed, we looked at some offline numbers in different user segments, and also kind of dig deep into the features. Why are certain features becoming more important? Is deemed as more important for the model compared to other features. But the whole space of AI, interpretable machine learning methods, I haven't personally looked into it, and in our team, in my team, that's not a part. But definitely, people are. We have a couple of interns who are thinking about ML fairness, AI fairness in the space of recognition. Do you have ML ops platform either built in-house or external to help iterate faster? We do have different teams. We do have ML infrastructure, ML systems, and then applied scientists. So there is in-house engineering and infrastructure teams to help us develop and iterate fast with machine learning models. How do you compare performance of ALS collaborative filtering versus deep learning network-based recommenders for e-commerce? In production last year, not me, but someone else had implemented ALS. And we were seeing some challenges with the results. And with any collaborative filtering, whether it's alternatively square or something else, the sparseness of the matrix becomes a big problem. More recently, we have someone in my team is working on neural collaborative filtering and more like other kind of approach. Let's see how it goes. But for now, we don't have any collaborative filtering in the part of the production system. Can you recommend an architecture that can be a good starting point for building our own recommender system? I mean, if you want to start building a recommender system, I think you should start with linear models. You don't have to go to deep neural network. Really starting with logistic regression, ensuring that your learning rate is good, your loss curve is converging, and having some good offline metrics in place to evaluate how your model is doing. And then tree-based models, honestly, a lot of our production system has tree-based models, which has worked wonders in our production system. So, and then you can, deep neural network, you can start building your own neural network with, starting with 1 layer and 2 layer and so on. So depending on your task. And otherwise, if you want to go explore the space of sequence model, that's different. So depending on how you're defining your problem, what kind of data you have, you could start building your model. But definitely if you're starting off in building a recommender system, start with linear model. They're much more interpretable. They're faster to debug and see if it's working well. And yeah, they're just easier to get started with. How does DS team keep up with the improving research in ML domain? Yeah, just keep working and keep studying, I guess. It is definitely a very fast-moving space. Even when I did my PhD, the whole attention-based models and so much advancement in neural network hadn't happened, even though I finished my PhD like 1.5 years ago. So yeah, I mean, I think it's a very, very, very moving field.
Okay, great. We have 1 minute left, and we have one person want to ask questions online. Hi, Mihai.
Me here.
Yes, go ahead to ask question.
Hi, Mamita. Thanks for the insights. I just wanted to know if there are any good books or readings which focus on the implementation part.
Implementation, I think so if you're looking at, for example, if you're looking for deep neural network implementation, there's recently this book I found on TensorFlow 2. I don't know if you can see. So deep learning with TensorFlow.
Yeah, I've got this. This is a good book.
Okay, yeah, that's a good book. So because TensorFlow 2 has a lot of difference in internal working, it's much better. Functional API and model support better than TensorFlow 1. In terms of recommendation system, we have some really nice books in this, but they are kind of focusing more on the algorithms and theoretical aspect. But in terms of implementation, I would say just if I have to pick a book, I usually Google and see what is.
The ones from PACT are good, so I'm on the right track. That means.
Yeah.
Okay, great. Thank you.
Okay, great. We are right on time. Thanks a lot, Momita, for the great presentations, and thanks everyone for joining us today. A lot of questions and discussions. This is great.
Thank you.
Okay, thanks.
Yeah,
thanks. Oh, by the way, one of the questions is asking for the slides. Are you able to share, or you can send to me, and I can just share to the attendees?
Okay, let's touch base.
Sure.
Right.